So first thing we're going to start with today is we don't have any warm-up. We'll just jump straight into it. We're going to start with SOHCAHTOA. Okay, SOHCAHTOA, remember that's sine is opposite over hypotenuse. Ka is cosine. We'll say it's the sine of theta, and cosine of theta is adjacent over hypotenuse. And then TOA, the last one, is tangent of theta is opposite over adjacent. So we're going to use SOHCAHTOA today to help us with trig functions on problems like this. So it says, the first thing the problem says today is let theta be any angle in a standard position and let x and y be the point where the terminal side of theta intersects the circle defined by the equation x squared plus y squared equals r squared. Okay, so what we're going to do here is x squared plus y squared equals r squared. That's actually something that should look somewhat familiar to us. Anyone know what that kind of looks like? Another formula that we've used before, or a theorem that we've talked about before? X squared plus y squared equals r squared. Hopefully it looks a little bit familiar. At the very least. What's it kind of look like to us? Yeah, it looks like the Pythagorean theorem, exactly. So that's the idea for this problem. It's the Pythagorean theorem. So it's like a squared plus b squared equals c squared. Oops, let's fix that. So the Pythagorean theorem. And the reason that is the case is because wherever an angle ends on its terminal side, so it starts with its initial side, and then it rotates, is what we've talked about on Monday and Tuesday, and then it gets to its terminal side, wherever it ends, technically you could draw a circle, and there's an xy point there. You can draw a triangle straight down from that point, or straight up from that point. We always form a triangle with the x-axis. That's really important. Never with the y-axis, always with the x-axis. And this is where SOHCAHTOA is going to come in. So never with the y-axis. That's important because some people say, oh, I could draw a triangle back to the axis this way. But you don't want to do that. So don't ever form one with the y-axis. Always with the x-axis. And when we're forming that triangle, technically we're using these coordinates like, hey, here's an x value, and here's a y value. And then the hypotenuse of the triangle is also the radius of the circle. That's where the letter r comes from. And that's why it's x squared plus y squared equals r squared. Because we're just taking the x value, the y value, and the r value to form the Pythagorean theorem there. That's the first important part of today's lesson, is that this is where this equation comes from, x squared plus y squared equals r squared. That also happens to be the equation for any circle, is x squared plus y squared equals r squared. That works for any circle ever, which is kind of cool. Now, what we're going to do next is we're going to evaluate the 6 trig functions and we've talked about 3 of them before. The other 3 we'll talk about in a second here. But to evaluate sine, you think about it as here's my angle right here. We're say that's angle theta. If the triangle, you always go from the angle that's forming between the terminal side and the x-axis. And we'll get to that, talking more about that tomorrow, what that angle is. But just think about that angle being formed. And you do SOHCAHTOA based on that angle. So opposite's going to be the y value over the hypotenuse, which is r. That's opposite over hypotenuse. Cosine would be adjacent, which is the x side, over the hypotenuse. And then tangent is opposite over adjacent. So the whole purpose of these trig functions is to help us find these x and y coordinates. Basically, if I have a circle with radius r, I should be able to sketch a triangle based on where that radius is, wherever it is on the circle. And then I can use SOHCAHTOA to find x and y values. That's the whole purpose of today. And we're just going to be practicing that today. That's really the goal. So the 6 trig functions that are here, though, we know 3 of them. We know sine, we know cosine, and we know tangent. So I'm going to write those out. Sine, cosine, and tangent. That's the longhand of them. The other 3 are called cosecant, secant, and cotangent. Cosecant, secant, and cotangent. So the way this works is you have sine, cosine, and tangent. Those are the 3 identities we're used to. Cosecant, secant, and cotangent. These are called reciprocal identities. Reciprocal identities. Those are reciprocals of sine, cosine, and tangent, respectively. And what does reciprocal mean when we're talking about fractions? So like if sine is y over r, what's the reciprocal of y over r? Any guesses? Reciprocal of y over r, remember what reciprocal does? You take a fraction and you flip it. So the reciprocal of y over r is r over y. That's exactly right. Nice. So that's what cosecant's going to be, r over y. And the same is true for cosine and secant. The reciprocal of cosine is secant. So that's going to be r over x. And then the last one, tangent, the reciprocal of tangent is cotangent. That's going to be x over y. Reciprocal identities. So cosecant is technically hypotenuse over opposite. Secant is technically hypotenuse over adjacent. And cotangent is adjacent over opposite. Those are reciprocal identities. We're just flipping the x and y values, or flipping the fraction, whatever the fraction is. Okay, that's how you do the other 3 trig identities. Now, some people get confused because they see sine and secant and they think the s's match up, and they see cosine and cosecant and think the c's match up as reciprocal identities. So the trick I use to not get caught up in that is thinking that every identity pair has one co in it, exactly one co. And what I mean by that is you have sine and cosecant. There's one co in that only. you have cosine and secant. There's one co in that. And you have tangent and cotangent, and there's only one co in that. So each identity pair has exactly one co in it. If you said, oh, the reciprocal sine is secant, then there's 0 co's, that's bad. If you said the reciprocal of cosine is cosecant, then you have 2 co's, that's also bad. You want one co exactly in each pair of reciprocal identities when you pair them up. That's how I remember which one goes with which. Exactly one co per pair. Okay? So that's the first part of what we're talking about today. Important note is that x and y can be positive or negative. And the way we tell whether they're positive or negative is basically what quadrant they're in. So like we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And where our example is, we have an x value that's going in a negative direction. So this is a negative x value. And then we have a y going in a positive direction. That would be a positive y value. That's how we tell whether they're negative or positive, basically by which quadrant they're in. That's how you tell whether the x values are negative or positive. Usually, if I give you an ordered pair, I'm going to give you a -1 or a +1, and you can just determine it by looking at the graph. Okay? But r, the radius, is always, always, always positive. Okay, radius is always positive because it's a measure of a magnitude. You can't have a negative radius of a circle. So that will always be a positive value. Okay, so r can be thought of as the radius of a circle or the hypotenuse of the right triangle. Both ways would be correct for thinking about it. The center of the circle is 0, 0, and the radius is r. All right, so whenever we're doing these circles, the center is always going to be 0, 0, and the radius is going to be r. Okay, now let's do an example. It says example 1, let -4, 3 be a point on the terminal side of an angle theta in standard position. Evaluate the 6 trigonometric functions of theta. So first thing we're going to do is I'm going to find the point -4, 3. So there's -1, -2, -3, -4, 1, 2, 3. So it's going to be over here. There's the point, -4, 3. Now, I'm going to go ahead and say, let's find our angle in standard position. There's our initial side. Our terminal side will go to that point 4, 3. And this is what our angle of rotation looks like from standard position. Now I want to draw the triangle to the positive x-axis, creating a right triangle here. I know already by looking at this graphically, the height of this triangle is 3 because the y value is 3. And the base of the triangle is 4, but we're going in a negative direction, so we're going to use -4 for our x. That's what I mean when I say x's can be negatives or positives, y's can be negatives or positives. But we don't know what the hypotenuse of this triangle is. But if I have 2 sides of a right triangle, how do I find the third side of that triangle? What do I use to find that third side? There's something I can use. And what is it? So 2 sides of a right triangle, what can I use to find the third side of that triangle? I should be able to use the Pythagorean theorem. X squared plus y squared equals r squared. A squared plus b squared equals c squared. Use that Pythagorean theorem to find the third side. In this case, x is -4, y is 3, and I'm going to find my radius right now. Negative 4 squared is negative times a negative. That's going to be a positive 16. 3 squared is 3 times 3. That's a 9. So I end up getting 25 equals r squared. Square root both sides, and r equals 5. R is always a positive number, so it's going to be a positive 5. There's no debate about that. So now I have my 3 sides of my triangle. That's how you find the radius, is you just use Pythagorean theorem. The next part I need to do, evaluate the 6 trigonometric functions. Basically, I just need to set up the ratios. So I'm going to say sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. All right, using that angle theta in there, that's going to be the interior angle. It's always the angle that's touching the x-axis is the angle I'm going to use. All right, and that's touching the origin, or formed from the origin and the x-axis and the hypotenuse. And I'm going to say sine of that angle theta is opposite over hypotenuse, 3/5. And cosecant is simply the reciprocal of that, hypotenuse over opposite. That's 2 of the 6 trig functions right there that I need to evaluate. Sine is going to be the y value, the opposite over the hypotenuse, the radius, 3/5. Then I do the same with cosine. My adjacent side is negative 4, and my radius is 5. For secant, it'd be 5 over negative 4. And then the last one, tangent, opposite over adjacent, negative 3/4. And then cotangent would just be the reciprocal of that, negative 4/3. That's how I would evaluate 6 trigonometric functions. You're going to be asked to do this on your homework tonight. So if I give you an ordered pair, can you sketch it, find the actual point where it's going to be located, and then draw a triangle, and now evaluate 6 trigonometric functions, set up 6 trig ratios for it. That's the first goal of the homework. All right. Any questions so far before we move on? So we used Pythagorean theorem to find the third side, and then we just wrote down our 6 trig ratios, and I just used SOHCAHTOA to figure out the first 3, and then I did the reciprocal to find the next 3. Okay, good. Next up, the unit circle. This is an important one. The unit circle is using that exact same formula we talked about before. Yes, we do need to write the theta after the sine, cosine, and tangent. Always write the theta afterwards. Okay, so good question there. Because it's always going to be sine of an angle. Okay, and eventually we're going to fill in that angle. Okay, so the unit circle is a circle defined by the equation x squared plus y squared equals 1. Just like before, it's going to have a center of 0, 0. But what's going to be different about the unit circle, it's going to have a radius of 1. All right, so that's why it's called a unit circle, because the radius is 1 unit. All right, and what happens is the values of cosine of theta and sine of theta are simply the x and y coordinates, respectively, of the point where the terminal side of theta intersects the unit circle. And I'll explain that. So what's happening here is we've got our x comma y values, and we'll go ahead and label it. There's our x, there's our y, and the radius equals 1. It's already listed there. So if we were to set up the trig ratios like we did at the very beginning on the first box, the sign would be opposite, which is y over the radius. But in this case, the radius happens to be 1, so it's just y over 1. So the sine function of theta is just the y value. This is why we like to use the unit circle. Cosine is going to be x over the radius. The radius happens to be 1, so it's x over 1. And it just becomes the x value. So what happens is cosine is the x value, and sine is the y value. All right. Oh, I did the colors backwards up here, so I'll switch those colors up here. Blue is cosine of theta, and green is sine of theta. There we go. So that's why the unit circle is something popular that mathematicians like to use, because now if I'm using a radius of 1 and I know what the x and y coordinates are, then I know what the answers to sine and cosine are pretty quickly. That's what's useful about that. And we're not really going to look at a good example of this today. We're going to save this part for tomorrow. But that's the idea with the unit circle. We might look at a couple quick things with the unit circle, like in example 2 with quadrantal angles, but that's about it. Excuse me, we'll get more into this unit circle later. So quadrantal angles, this is something that is a multiple of 90 degrees or pi over 2 radians. So that's what a quadrantal angle is. A multiple of 90 degrees or pi over 2 radians. Okay, and basically what that means is you take any angle and you're going to end up on an axis with a quadrantal angle. So 0, 90, 180, 270, and then 360, 450, 540. All right, and it's going to keep adding 90 each time. So just some examples of quadrantal angles. You could just say 90 degrees is one, negative 450 degrees is another one. Oops, negative 450 was already given. Let's say negative 360 degrees. All right, so any multiples of 90 would be an example of a quadrantal angle. 720 degrees would be one. And the same thing is true with with radians. That first radian measure should be 3 pi over 2. But basically with radians, as long as it's either a whole number or a fraction over 2, that's an example of a quadrantal angle in radian measures. So I could say 5 pi, I could say 49 pi over 2. Because it's over 2, I know that's going to be a multiple of 90 degrees essentially, but in radians form. I could say negative 13 pi over 2. That's another example of a radians that is a quadrantal angle, a multiple of 2. Okay, and that's the idea for these types of problems. Okay, so a lot of new vocabulary today. Unit circle, we've learned about these reciprocal identities, and now this quadrantal angles, but quadrantal angle just means multiples of 90. And this is how we use a quadrantal angle. When we're dealing with a unit circle problem, that tells us the radius is 1. To evaluate a trigonometric function, it says theta equals 270 degrees. So positive 270 degrees, that is an angle of rotation, which we've talked about on Monday and Tuesday. So I start on the positive x-axis and I rotate 270 degrees. And it looks like I'm going to end down here. And basically what it means is if I were to draw a circle on here, my unit circle, and I said the radius is 1, I want to know what are the coordinates of this point down here. I know the center of the circle is going to be 0, 0, but what are the coordinates of that point down there? If the radius is 1, I'm exactly 1 unit away and I'm going straight down. Any guesses what the coordinates are going to be? Just think about XY coordinates on the circle. I'll give you a hint because I'm going straight down. The X coordinate's actually not going to be changed. And the Y coordinate is going to be a 1. The question is it going to be a positive 1 or a negative 1? Because of the direction I'm facing. Positive 1 or negative 1? And turns out it's going to be a negative 1. And that's where I get my X and Y values from for this unit circle problem. So unfortunately what happens here is I cannot draw a triangle here just because I'm on a quadrantal angle. And that's why I want to use the unit circle instead, because what the unit circle allows me to do without drawing a triangle, I'm able to come up with an ordered pair of X and Y values and say, I want to use that 0 and that negative 1 when I'm evaluating the 6 trigonometric functions. There's sine of theta, there's cosine of theta, and there's tangent of theta. Those are 3 of them. And then there's cosecant of theta, there's secant of theta, and there's cotangent of theta. And we do the exact same thing that we were doing before. We can say, well, technically, sine is the y value over the radius. Oops, the y value in this case is negative 1 over the radius, which was just 1. Or, like we talked about up here with the unit circle, it's just going to be whatever the y value is, negative 1. And then that means cosine is going to be the x value, which is 0 over the radius, and 0 divided by 1 is just 0. And then finally we have the opposite, which is the y value divided by the x value, negative 1 divided by 0, and unfortunately, whenever you're dividing by 0, that is undefined. And I don't say equals undefined, because it's not really equals undefined, it's just undefined. It's impossible to divide by 0, so I just write tangent of theta is undefined. Okay, that's how I'd write that one. And then for reciprocal identities, I could just flip them over. This one's going to be a 1 over negative 1. So cosecant is also going to be a negative 1 here in this situation when I do the division. Secant is 1 over 0. That's another one that's just going to become undefined because I can't divide by 0. And then cotangent is 0 over negative 1. And that's going to equal 0. And that's how I would evaluate the 6 trigonometric functions on something like the unit circle. Kind of weird, because this time I can't see the triangle, so I have to go with my knowledge that we did just a few minutes ago before. No, and I'm going to use the y value for the sine and the x value for the cosine. And then I'm just doing reciprocals for cosecant and secant. All right, and then tangent's just y over x, and then cotangent is x over y as a result of that. Now, I'm going to give you guys a couple minutes. I'm going to give you at least 10 minutes to work on these 4 problems here to try and practice this. I'm going to tell you right now, problem 1 is a tricky problem, and it's just because when you solve for r, you're going to get a radical answer, and I want you to leave your answer as a radical for the radius. So leave r as a radical. You might want to skip number 1 first and try 2 and 3 before it. I think 2 and 3 are going to be a little bit easier than number 1. Just telling you right now. And then come back to number 1 once you feel comfortable with problems 2 and 3. But leave your r answer as a radical and try and work with that radical to solve for problem 1. That's the advice I can give you for that problem. I'm going to start a 10-minute timer now, so take your time, you guys, and then we'll take a look at these problems together. If you have any questions at all, please let me know. Then for the second part, it should be -8 over their hypotenuse of 17. And then for the tangent function, opposite 15 over adjacent -8. And then cotangent would be the reciprocal of that, -8 over 15. That's what I'm looking at for these types of problems, evaluating the 6 trigonometric functions. So you need to use Pythagorean theorem to find radius, the third side, and then we just set up those 6 trig functions and solve. Okay. For problem number 3, we'll do the same thing. Set up all 6, sine, cosine, and tangent. Cosecant of theta, secant of theta, and cotangent of theta. And again, sine is opposite over hypotenuse. Hypotenuse is always a positive number. And that means our trig ratio becomes -12/13 for sine, -13/12 for cosecant. And then cosine is going to be -5/13. And its reciprocal is going to be -13/5. And then last but certainly not least, tangent, -12/5 over -5. That one will actually need to be simplified a little bit because we have 2 negatives. So it's actually going to become 12/5 when it's all simplified. And that means its reciprocal is going to be 5/12. And that's what problem 3 should look like. So 5/12 and 12/5 for tangent and cotangent. If you can simplify, please do. That's really important for these types of problems. Now let's look at number 1, because this one's a tricky one with that radius the way it is. We set up our trig functions. Sine of theta, cosine of theta. We'll just start with these 3. Tangent of theta. Now when I do sine, what's going to happen is I will do -3 over the hypotenuse is 3√2. And I can simplify that. -3 over 3√2, I can divide a 3 out of both terms. So I should technically get -1 over square root 2. And I don't want radicals in the denominator. So this is something that we talked about in mod 5, getting rid of radicals in the denominator. So I'm going to multiply both numerator and denominator by root 2, which is just a 1. And I'm going to get root 2 times negative 1, that's negative square root 2, over root 2 times root 2, which is root 4, which simplifies to 2. So my sine function is negative root 2 over 2. All right, so yeah, there's a lot of simplification that goes on there for that particular problem, and that can make it a little bit tricky. And cosine is going to be very similar to this one, except it's going to be a positive answer instead of a negative answer. So this time I get a 1 over root 2, and when I multiply by root 2 over 2, I'm going to get a positive root 2 over 2. So a little bit simpler than sine. And then last but certainly not least is tangent. We're going to do negative 3 over 3, and that simplifies to negative 1. So tangent is actually not too bad. But then I have to do the 3 reciprocal identities, which I don't have a ton of room here. Oops, so we'll go ahead and start with cosecant of theta, and then secant of theta, and cotangent of theta. To do the reciprocal identities, I would start by saying, let's do 3 over root 2 over negative 3. And this one's actually a little bit easier than the previous one, because I can divide both sides by 3, and I'm left with square root 2 over negative 1, so I can just rewrite it as negative square root 2. So that one actually is a little bit simpler to simplify than the sines and cosine ones. And now for secant, I can rewrite that as 3 root 2 over 3, and that simplifies to positive root 2. And then last one, cotangent, 3 over negative 3, and that simplifies to negative 1 as well. So that's what problem 1's going to look like when it's all simplified. And that one, like I said, is a really tough one because of the radicals involved. But sometimes we're going to have to deal with radicals in these problems. We're not always going to have numbers where the hypotenuse comes out to a nice, easy number. So we do have to be used to dealing with radicals and getting them eliminated from denominators of fractions in situations like this, like problem 1. And last, but certainly not least, problem 4 says use the unit circle to evaluate the 6 trig functions at theta equals negative 180 degrees. So we start there, we rotate 180 degrees, means we're going to end over here in this quadrant at this point here. And that point is, negative 1 on the x-axis and 0 on the y-axis. So being able to draw the picture and come up with the ordered pair is super important for these types of problems. And now we can go ahead and try and set up our trig ratios. And for sine, it's going to be the y value over the hypotenuse, which is just 1. And remember, we don't necessarily need to write that. We could just say it's the y value, and cosine could be the x value. I'm just writing it to show you where it's coming from. For cosine, it's the x value over the hypotenuse. And then these will simplify. So sine is just 0. Cosine is negative 1. And then tangent is the y value over the x value. And in this case, that becomes undefined. So tangent, not going to give us anything there. Undefined. And then when we do reciprocal identities, cosecant is also an undefined function because we get it divided by 0. Secant is 1 over negative 1, so that's going to simplify to negative 1. And cotangent is 0 over negative 1. Again, I'm just using the reciprocal of whatever tangent was. and that's just going to become a 0. And that's how I'd evaluate something like problem number 4 there.